Assalamu alaikum. How are you, my dear students? Hope you will be hope you will be fine and okay. I welcome you all into my today lecture. Today is our lecture number 35, Unit 16, Physics of Solids. In our today lecture, I will tell you about the structure of the crystal structure, elasticity, deforming forces, deformation, elastic limit, plasticity, stress, strain, Hooke law, elastic modulus, and its type, right, are the today's topic. So let us start with our topic today. First of all, the about the crystal structure. The crystal structure. The crystal structure is revealed through X-ray diffraction through the process of X-ray diffraction. X-rays diffraction. When the crystal or the given substance is exposed to X-rays, right, then the structure can be revealed by the process. This process is known as X-ray diffraction. The question is that why we use X-rays as a probe to reveal the structure of the crystals or solids, because of the reason that the wavelength of the X-rays due to is extremely small. So due to its extremely small wavelength, extremely small wavelength, they are used to probe the structure of the solids. Why? Because in solids, the intermolecular spacing is nearly equal to the wavelength of the X-rays. This, the lambda is equal to the intermolecular spacing. This D is the intermolecular spacing, right? So this is one of the reasons that we use the X-ray diffraction. The crystal structure, first of all, that I will tell you that the crystal structure is obtained when a basis is added at each point. Crystal structure is obtained when a basis, later on I'll be telling to you what is basis. When a basis, this is why I underline here, when a basis is added, at each point, at each point, then we obtain the crystal, right? So crystal structure is in fact equals, that we can say about the crystal structure, that any crystal structure can be obtained, this crystal structure equals the crystal lattice, the crystal lattice plus the basis structure, right? They forms the crystal structure. Now let us first, I would like to tell you that the crystal structure, this crystal structure is in fact what? It is the atoms in 3D array. In solid state physics, the crystal structure is what? It is the atoms the atoms in 3D array, in 3D array, three-dimensional array, in three-dimensional array. This group of atoms, since this is a group of atoms in 3D array, so this group of atom we call the basis or the unit. So this group of atom, the group of atoms in this 3D array is called the basis, is called the basis or unit, is called the basis or unit, right? As you see here in this diagram, this is a unit cell. Later on I'll be telling to you that what is it. Look, so this is what, this is the basis, right, in 2D, and here it is in the 3D. Here it is in the 3D, this whole one, right, like this one. So this is called what? This is called the basis or the unit. This is why I told that crystal structure is equal to a crystal lattice. Later on I will be telling to you that what is the crystal lattice, right? And then the basis, and so basis is the group of atoms, as I told, like this one. So this atom, this atom, this atom, and this atom. So this group of atom is called the basis, or sometimes we call it the unit also. So you must remember this one. Now this basis is repeated at regular interval in all direction. Repeated at regular interval. Repeated at regular interval in all direction. In all direction. Repeated at regular interval in all directions. So here you see, look, in this case you see that this is repeated. This is a unit cell, and in two-dimensional system you see that it is repeating itself, as you see here, 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 and here, like here. So you see that there is repetition. There is what? There is repetition. So that is the repeated regular, that is that bases are repeated at regular interval in all direction. Here you see in three-dimensional structure also. Look, in three-dimensional structure here it is, you see that it is just repeating itself, right, in all direction for the given crystal. So one is this very important point here. The second important point here is that for the geometrical analysis, 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 an imaginary array of points is in space is introduced. We introduce an imaginary array of points, an imaginary array of points, an imaginary array of points. I will explain this also. An imaginary array of points in space is introduced. In space is introduced. This, for this geometrical analysis, this array of points, it replaces what? Replaces basis. Replace the basis. So the basis. So instead of the group of atom, we just use a point in space. So in fact, these points are dimensionless and shapeless entity. These are what? Dimensionless and shapeless entity. And shapeless entity, which represents the given unit. So here you just see, look, the geometric array of points. Here you see these points. Look, this point, this point, this point. So actually these points replaces what? The bases. And you know, as I told, bases are the units, basic units. So for their clear geometrical interpretation, we replace bases by points, right? And the right, then this together all form lattice. So we introduced a term here. The term we call the lattice. This is also very important, lattice and a lattice site. Now what is lattice? Lattice is the collection of infinite points in periodic arrangements. Collection of infinite points, collection of infinite points in periodic arrangement, in periodic arrangements. Let me create some space for myself. If I miscalculated, that I could finish it. Okay, so this is the collection of infinite points in periodic arrangement. So here you see that, look, this is the two-dimensional lattice. Here you see this is a lattice, right? This whole infinite array of points is called the lattice. So this is the lattice in 2D, and we have the lattice in 3D also. Each point, this point which we defined earlier, shapeless and dimensionless, that is called the lattice site. So lattice is the collection of infinite points in periodic arrangements, where the lattice sites, now what is this lattice? First let me tell you that the lattice is in fact the geometrical framework for the crystal structure. Geometrical framework. It is what? It is a geometrical framework for the crystal structure. So the lattice site, as I told, that the points which form lattice are called the lattice site. So lattice site is what? The point, which forms, the points forming the lattice. The lattice, yeah, which contributes to the lattice is called the lattice site. Is called the lattice site. So here you see it, as I label it or mark it, this one, this one, this one. Here they are called the lattice site. Clear? Then there is another important point, and we call that point as the lattice constant. The latest constant. Now, what is the latest constant? The latest constant is the distance between two consecutive. It is the distance between two consecutive latest side. The latest side. The latest side. The latest side is called the latest constant. It is called the latest constant, and it is this latest constant which is comparable to the wavelength of the X-rays. So this is what the latest constant is. This distance, see here, this to this distance. This distance is called the latest constant. Similarly, this one and this one. So these are called the latest constants, right? Then there is the unit cell. Another important point, most probably the last point regarding the crystal structure, which contributes to the crystal structure, is the unit cell. And I told that I'll be going to tell you that what is this unit cell. So unit cell is the smallest geometric unit. It is the smallest geometric unit, the smallest geometric unit, of which formation we have discussed already, the smallest geometric unit which forms crystal. Sorry, which forms crystal in 2D or 3D, in 2D or 3D space. Okay, so here these are called the unit cells. So here this is the simple cubical unit cell, the crystal structure which forms. This is the body centered cubic cell, and this is the face centered cubic cell. So these are some unit cells which you can see here. Clear? So that is all about the crystal structure. Right now, apart from the crystal structure, we have the apart from the crystal structure, we have the elastic module. Elastic module. Now we want to study the elastic moduli, right? Here, how the given crystal responds to stress, like that. Here we need to know about the elasticity, and I'll not be explaining elasticity to you too much because you already know about elasticity. And then there is deforming forces, and then deformation. Then there is deformation, and we have the elastic limit also. The elastic limit, and we have the elasticity, right? And we have the stress and strain. These are very important points. Stress, strain, Hooke law, the Hooke law, and the elastic modulus. In the elastic modulus and its types. So we will discuss those things here, inshallah, in some detail. Now, what is elasticity? Elasticity is that property of material of substance by virtue of which it can regain its original shape and size after when the deforming force is removed. Deforming force. Now, what is this deforming force? Deforming force. Deforming force is the force which has the ability to distort the shape of an object, the shape or size of an object. We call that deforming force. In solid state physics, we call this deforming force as stress, right? So actually the deforming force is in fact a kind of stress, and deformation is the change caused by the deforming force. And in fact, this deformation is, you have studied in class 9, it is in fact the strain. So almost all of the material are elastic in nature. The elasticity of the material depends on the nature of that substances. Different substances are different elasticity. For example, steel is more elastic than rubber. In class, keep one thing in your mind, that elasticity is actually not stretching or compression. Elasticity is the property of regaining or gaining its original shape and size back once the deforming force is removed, right? So if you stretch the rubber, you distort the shape of the rubber. Similarly, this is applicable to other kind of material also. Elastic limit is the limit, or it is the stress beyond which the body is unable to regain its original shape and size even when the deforming force is removed. So that is known as the elastic limit. Usually the elastic limit determines the strength of the material. So beyond, if you increase the stress beyond the elastic limit, then the substance changes into, there occur plasticity, right? Or we say that the material tends to become plastic, and that is, what does this means, plastic? That it remains in deformed shape, right? Now another important point is stress. So you already know about the stress, and I would discuss this little here because since class 9 that stress is the perpendicular force acting per unit area of an object. The stress is measured in Newton per meter square. Okay, so it is the force per unit area which can distort the shape of an object. So that is called the stress. And the strain, you also know that strain is in fact the it is the deformation produced in object due to stress. Although strain is different, there is the longitudinal strain when we count the changes in length. Then there is the shear strain also, that if we look to the changes in area, and there is the bulk strain also, which is the change in the volume of an object due to stress. But here simply I would like to write to you for the longitudinal strain, the change in length to the original length of an object. So what does this really mean? This means that the frictional increase, that strain is the frictional increase in the length of an object due to stress. This is called deformation, right? It has no unit. This is unit, and or we can say that a dimensionless quantity because it is the ratio between two similar quantities. Then there comes the Hooke law, and you are very much familiar with the Hooke law, but I will explain the Hooke law inshallah in the coming lecture, okay, in detail. But Hooke law is telling to you that within the elastic limit, the strain produced in the object is directly proportional to the stress applied, right? So that is the Hooke law. And the elastic modulus is in fact the ratio of stress to strain is called the elastic modulus. So elastic modulus is the ratio of stress, any kind of stress, to strain, any kind of strain, right? But remember that within the elastic limit, this all happens within what? Within the elastic limit. Within the elastic limit, right? The ratio of stress to strain is directly proportional to each other. Okay, now this elastic modulus, elastic modulus, there is three types of the there are three types of the elastic modulus, right? One we call the Young modulus. The Young modulus. The Young modulus, or simply we denote this by Y. We have the shear modulus, and the shear modulus I will explain in bit detail because this wasn't in your class 9 or modulus of rigidity. This is the shear modulus, and shear modulus is denoted by S. In this shear modulus, this is denoted by Y, and this is caused by a force tangential to one of the face of the objects. It is the caused by what? Caused by our shear strain. We can say that it is because of the shear strain, and that shear strain is caused by a force tangential caused by a force tangential to one of its face, so this comes due to the tangential forces. And then we have the bulk modulus also, the bulk modulus. Now, what is the bulk modulus? Bulk modulus is due to what? The bulk modulus, it is due to the change in the volume. Due to what? Due to, in this one is due to change in area, due to change in area. This is due to change in length, due to change in the length of an object, tensile strain, right? And this is due to the change in volume, Now, what is the Young modulus? Young modulus tells you that the Young modulus is the ratio of stress to strain, provided that the elastic limit does not exceed. So in order to explain to you the Young modulus, let us consider that if we have an object, right, for example, a rod of length L, this is the length L of the rod. If it is subjected to a stress, right, this is a stress force per unit area, and this is the cross-sectional area, as you see the cross-sectional area of an object this way, right? And here you have the force also. So here you see that a force acting per unit area, this for it can be stretching also, and it can be compression also. Here I demonstrate it as the stretching. So when you stretch the objects, since volume will remain the same, so the length increases, area of cross section decreases, and that is under force per unit area, stress force per unit area. And you see that, look, what is going to happen, that there is an increase in the length of an object, and this is the final length of an object, LF, and that is L naught, and that is LF. So this change in length, delta L, LF minus L naught. Okay, so now you know that that the, if you just see, look here, that the stress is force per unit area, so Young modulus force per unit area, and the strain is the change in length to that of the original length of an object. L naught, or just simply you write L, so F into A, let we write just L on L is enough to indicate the original length. So force per unit area, and then there is this L by A, right? So this Young modulus determines the strength of that material. So your Young modulus is FL into A, this is, yes, L by delta L into A delta L, right? So that is the Young modulus, where delta L is the change in length, right? So you can find the change in length like delta L equal FL into AY. This determines the strength of the material, clear? So it is different for different substances. Now the next one, as I told, which is important, is the shear strain, the shear modulus, the shear modulus. As I told, that the shear modulus is caused by what? That the shear modulus is caused by the tangential forces, which acts along the surface parallel to one of the surface of the object, which is clear from the this here. Now you know that this shear modulus is equal, the shear modulus, the shear modulus is the shear stress divided by shear strain, right? Now they here, this will be the shear modulus S, as I told, it is denoted by S, and here it will be the shear stress, and here it will be the shear strain. Now for the shear stress, what will be this shear stress? The shear stress will be equal to this force, as you see here, and this force F per unit area of an object, as you see, like this one. And the shear strain can be, the shear strain The shear strain can be written as displacement of the shear face, displacement of the shear face divided by the displacement of the fixed displacement of the fixed face. So here this in the diagram, look under the stress, right, under the shear stress, here you see that, look at this displacement. This is the displacement of the shear face, right? The displacement of what? The displacement of the shear space, the shear face. Why? Because the force is applied here and it caused this displacement. So you see that this displacement is in fact delta x, right? And that for this reason, see here that there is the delta y, the displacement of the fixed space, as you see. This is the fixed face. So this displacement is what? This displacement is delta y. Now if you just look to the triangle, and if I just make it like this, as you see here, then this is theta, and you see this is delta y, and you see that this is delta x. So you see here that we see that the tan theta is actually equal delta x by delta y, right? So here this is nothing but it is the tangent theta, right? This is called, where theta, we call the theta as this theta as the angle of shear, the angle of shear. We call this the angle of shear, and this angle of shear, so because of this angle of shear, we can write it that S, the shear stress, is equal force per unit area. And since it is equal to this delta x by delta y, so instead of this I can write FA into tan theta, right? Or in other words, we can write that S equals F into A tangent theta, right? Or we can write that F equals A theta, where that is that for small value of theta, tan theta always equal to theta. So this is how we can calculate the shear modulus, right? For the bulk modulus, this is very easy, and I don't want to explain it because this is what you can know from your class now. Bulk modulus. In the bulk modulus is it is the ratio of what? The bulk or the volume stress, bulk modulus. The bulk modulus is the volumetric stress, divided by the ratio of volumetric stress to the volumetric strain. And now what is that volumetric stress? Again, that is force per unit area, and it is the change in volume per unit volume. So the frictional increase in the volume of an object due to stress, volumetric stress, is known as volumetric strain. And they are all measured in the same unit, remember. So it will be equal to F A V into delta V. And whether if it is all kind of the elastic moduli are measured in, sorry, I should tell you this before, measured in Newton per meter square, and they denotes the ultimate strength of the material. So for the bulk modulus, which is represented by B, and this bulk modulus can be written as F into V, uh, F into V uh, into A by delta V, right? And that is the bulk, that is for the bulk modulus. Now it depends that whether, look, see here, that we can also write in term of pressure. If you just call force per unit area as pressure, then it will be what? It will be pressure delta P into delta V by V. If it is Young modulus or if it is a bulk modulus, can be both positive and can be both negative. Positive when there is stretching, and negative when there is compression, right? Because if you apply forces from all other side like this, for example, see here, look, if you have this object like this, see here, as you see. Now, if there is what? If there is the force is acting on it like on this, for example, here, 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 and here like this. So what is going to happen? The object is going to compress, and the original or the new shape which it can regain could be like this. Okay, so you here see that the object is being what? The object is being compressed, and this bulk modulus will be negative, right? But if you see that if you produced another kind of forces like stretching forces, then what will happen for the stretching forces? You stretch here, you stretch here, you stretch here, and you stretch here, and the new shape of the object would look like this, right? The volume will increase, and this will be taken as positive. As you see, this will be the new uh, shape of an object. So this is our today lecture. Thank you very much for being here. Inshallah, see you in the next lecture.